All right, today's topic is binomial probability distributions. In all of Chapter 7, we talked about random variables and probability distributions, and this outside bubble is all random variables. So write down how many cats everybody has, or write down how many siblings everybody has. There's discrete and continuous and so on and so forth. There are two groups of distributions that we are going to study next. There are binomials, which is today's topic, and there are geometrics, which will be next time. And I first just wanted to make this diagram to show you. This is just a special case of all of the random variables that we've been dealing with. So what makes it binomial? A binomial question would be one like this. Actually, here's one example. You have 5 questions on your test left. Each one's multiple choice with 5 answers. You have to guess on these 5. You don't know. What's the probability that you get 2 of them correct? Binomial, the bi or the 2, comes from the fact that we're going to have trials with 2 outcomes, either a success or a failure. And that's one of the characteristics of a binomial. So a binomial distribution or a binomial random variable will have a fixed number of independent trials. So you'll notice in the question, it's going to say you are going to try this trial this many times. I told you you have 5 questions left. This is not like I'm going to go out and shoot free throws until I make one. That's going to be geometric, and we'll get to that later. We know how many times we're going to try this thing, and each trial is independent of the previous one. It doesn't matter whether I get a question right or wrong on this test. That doesn't affect my next question. The probability is the same every time. And that seems like it might be the same thing as independent, but what this takes care of is you can't say I've got 10 questions, 5 multiple choice with 4 answers and 5 true false. You can't mix up the probability of succeeding every time. We next have, let's just put this into 3 total. We either succeed or fail every trial. And the question that's going to be asked is this. What's the probability, you write it in probability notation, the probability of our successes out of n trials. So do anything 10 times. Shoot a basketball, flip a coin, consider, a success and a failure and see how many times you succeed out of 10. Now, success and failure have a positive and negative connotation. The positive outcome doesn't always mean a success. For instance, if I ask 10 people, do you or do you not smoke crack? If they say, yes, I smoke crack, that technically is a success because they answered with the positive answer, yes. Obviously, that is not a success. So don't get hung up on success and failure being the good and the bad outcomes. All right, so let's go on to how we figure out these probabilities. We'll use this as our example. If you're going to get 5 questions, you're going to answer 5 and get 2 of them right. That means you had to multiply the probabilities of getting it wrong, which is 4 out of 5 times. Here's one example, 4 out of 5. Let's say I get the first one wrong, the second one wrong, the third one right, 4th one wrong, and the 5th one right. A lot of people, if I just give you this question before you know about probabilities and binomials, you would give me this, and I believe this equals 0.02048. The problem with that is this is one specific sequence of rights and wrongs that you could have gotten. But you also could get many different possibilities of right and wrong. So what the binomial formula has in it is a way to count up all the different possibilities of where your successes go. I've got 5 questions. and I need to, in a sense, choose which two are going to be my successes. Now, during the test, you aren't choosing which ones you want to get right, but at this stage, I can choose where the two 1/5ths go. For that reason, we're going to use a combination. The binomial formula is like this. My variables, n, number of trials, whether or not you wrote down this example, write down these variables. R is the number of successes. P is the probability of success, and this will stay the same through every trial. By the way, on your AP formulas, I believe they use K instead of R, but don't let that throw you. They use 1 minus P as a probability of failure. I like to use Q sometimes. It's the opposite. If I have a 30% chance of success, then I have a 70% chance of failure, and so on. So Q, which is 1 minus P, whichever one you want to use is fine. Your formula sheet will say 1 minus P. It's a probability of failure. So for all of these possible sequences of success and failure, I need to take the probability that I succeed, and I need to raise that to the power number of successes. Then I'm going to fail all the rest of the times. If I have n trials and I succeeded r times, then I'm going to fail n minus r times. So this is like what I have listed above with the 4/5 and 1/5. But I also have to account for all the different arrangements of those 4/5 and 1/5, where I, in quotes, choose which ones of my trials are going to be successes. That's NCR. We've talked a little bit about combinations in class. This is in your calculator. It's, I hope you understand what it means, but using the formula for us and for your AP test is the important part. Another way to say NCR is NR in parentheses with no fraction bar. P to the R, Q to the N minus R. So this is just a different way. So if I want to answer this question above, I want to try something 5 times, succeed twice. This could be 5C2 as well. I have a 1/5 chance of succeeding, and that needs to happen twice. I have a 4/5 chance of failing, and that's going to happen 3 times. 5 choose 2 happens to be 10, which means that that number I had above, I just need to multiply by 10 because there are 10 different arrangements of 3 failures and 2 successes, which makes that easy to multiply. So I have about a 20% chance that I get exactly 2 right. Think about all the options. If you answer 5 multiple choice questions with, well, it doesn't matter how many options in this case, we would create a little distribution. Now this is what you've been dealing with, but previously I would just give you these numbers, and now you might have to find them. Think about this distribution. These are all possible cases of how many you would guess correctly if you had to guess. What I found was this one right here, and you could find all the other ones similarly. I'm going to show you in your calculator how I could get that value. If you go to distribution, which is second vars, and you go to binomial PDF, this is a binomial probability density function. The inputs are NPR, like National Public Radio, the old school radio station with all the news on it. N is number of trials, 5. P is probability of success, 1/5, and that can be a decimal or a fraction. And R is the number of successes, 2. And there's my 0.2048. So that will do that formula all on its own. You don't need to worry about it. If you were just going strictly by the formula, you could go in and get the NCR, and I can show you how to do that, but I'd rather you be familiar with binomial PDF. One more thing, in my stats, in my list, I'm going to go into list 1 and 2. Actually, 1 is almost set up right. I'm going to have 4 and 5 as my other options. You can go into 2, clear it out, and then go program list 2 to give you all the separate binomials. So I'm going to program list 2 with distribution, binomial PDF, NPR. So I have 5 trials, 1/5 probability of succeeding. And here's where I'm going to do my little program. I'm going to let list 1 be the number of successes, and that should give me my complete distribution really quickly. And you can see the 0.2048 right there with the 2 successes. One other calculator note. When you go to distributions and you see binomial CDF, that's a cumulative density function. Watch what happens. 5 trials, 1/5 probability of succeeding, list 1. This will accumulate. This will tell me what's the probability that I succeed this many times or less. So look at my numbers now. I've got 0.3, 0.4, 0.2, and then they start getting smaller. Look what happens when I do this. Now I get 0.3 still for 0. 1 is 0 plus 1, because this is cumulative up through 1. 2 is 94, which is the 0.3, the 0.4, and the 0.2. And then it will always end in 1, because 100% of the time, if I have 5 trials, I will succeed 5 times or less. So make a little notes on how to get this stuff in your calculator, and let's move on. Okay, the next thing you need to know is what are the mean and the standard deviation of these distributions. We've spent some time, and they're a lot harder if they're not binomial. Remember how we did mean and standard deviation? We would have to make that complete chart, do all the squaring and multiplying and adding and square rooting, and we did that full chart in section 7.2, and we found the mean and standard deviation. If it's binomial, that process is a lot easier. 2 formulas. Make sure you get these down. Mean and standard deviation. Mean, no big deal, NP. What that means, if you want to know on average how many of these questions you're going to get right out of 5, take how many there are, multiply by the probability that you succeed, and that's your number. All right, so for my example above, how many questions do I expect to get right if I'm just guessing? Well, there are 5 of them, 1 out of 5 shot of getting it right, so I'd expect to get 1 right. Does that mean I always get 1 right? No. That means 1 is a pretty likely outcome, and it also means that if I were to try this thing over and over and over again and guess 5 questions repeatedly, sometimes I would get 0, sometimes I would get 1 and 2 and 3, occasionally I would get 4 or 5 right. If I average all those 0s, 1s, 2s, 3s, 4s, and 5s together, I should get 1 in the long run. All right, this is what I expect to happen in a long series of trials. Standard deviation, square root of NPQ. Doesn't have, as always, it doesn't have quite the real world significance, but it's still easy to use. The standard deviation of the number of questions correct will be the square root of 5 times 1/5 times 4/5. I don't have a calculator handy, so I don't know what that is, but type that in if it makes you happy. Square root of NPQ. Still easy. Doesn't quite mean as in the real world what the mean does, but we should be used to that with standard deviation. So these are the mean and standard deviation of binomial. Make sure that you have those written down. A lot easier than that big chart full of all our steps to find the mean and standard deviation of a regular random variable if it's not binomial. All right, so that's it. This is binomial. We have a specific type of random variable where we are counting successes out of a fixed number of independent trials, and the formula of the day that you need to make sure you have is right here. All right, n choose r, p to the r, q to the n minus r, or binomial PDF NPR. All right, so I'm curious, out of 33 students in your class, what's the probability that 25 or more actually watch this video? Guess we'll see. Young out.